Unit 7, Chapter 25, chi-squared, homogeneity and independence. All right, the homogeneity and independence test are run identically on the calculator. The only difference is the ho and the ha, the null and the alternative hypothesis. So I'm going to demonstrate those, the theory behind it, and then two problems. All right, this is just reviewing the chi-squared goodness of fit. Remember, with the chi-squared goodness of fit, you're actually going to, with the chi-squared homogeneity, have the exact same equation as far as the chi-squared statistic, the test statistic. And that's why I see it's called the chi-squared test statistic. But remember, with the chi-squared goodness of fit, we put all of our data into a spreadsheet, and we had to put our observed data and our expected data into a spreadsheet. We had to run a chi-squared goodness of fit, and what it was doing is seeing how good the fit was of the data we had. It was very similar to a one proportion z-test, except a one proportion z-test just did one proportion. For instance, it did blue M&Ms measured to blue M&Ms proportionally, the sample versus the proportion to the actual population. But the chi-squared goodness of fit not only does blue M&Ms, but does red, yellow, blue, green, etc. So it does all of them. So that was our chi-squared goodness of fit. And if you need more information on the chi-squared goodness of fit, I have a whole video on that. Make sure you see that video. Okay, so now moving to the chi-squared homogeneity and independence. Another name for that is called a chi-squared two-way test. So when it comes to naming your test, you can call it the chi-squared two-way test because you have it for independence and for homogeneity. College Board does accept chi-squared two-way for both of these, because in your null and alternative hypothesis, you're actually going to be determining which one it is, the homogeneity or the independence, just by your language. All right, so it's called a two-way test just because it has one thing here, and there's your data, okay? All right, with our null hypothesis is that basically for both of them is that there's no difference among the proportion, and the alternative hypothesis is that there is a difference. So we are going to have to do our expected count. So remember, in our chi-squared goodness of fit, we had expected count and we multiplied our total times the percentage. Well, this is going to be similar to this, and I'll demonstrate for you in a bit, but the expected count formula is the row total times the column total divided by the table total, and I'll show you that in just a bit, but this is just the theory behind it. This is the same chi-squared test statistic, observed minus expected squared divided by expected, and I do expect to see this on your test and on College Board. Degrees of freedom is rho minus 1 times column minus 1. And remember, the p-value of chi-squared statistic is shaded from the right. And of course, again, reminding you, this is the chi-squared, sorry, it's kind of ugly. It starts at 0, and of course, all the chi-squared statistic goes further, or gets bigger as it goes to the right, but the p-value shaded from the right. And so as the chi-squared statistic gets bigger, this is, of course, the p-value decreases. All right, so let's go ahead and see what's the difference from a homogeneity, because that's what I'm going to start with. So for a homogeneity, let's go ahead and see this. The homogeneity group, basically, for a chi-squared homogeneity, again, you can call it a chi-squared two-way test, but for that, you have two or more populations, and you're trying to see if they are the same, if one variable that I'm measuring is the same. So for today, what we're going to be doing gummy bears, and I have two different populations, Haribo and Meyer. So those are my two populations, and I'm trying to see the variable that I'm using as color, and I'm trying to see if the Haribo or Meyer populations are the same in the color distribution. These are the categories. So I have all these categories, and these are the populations. One population, the second population. For the degrees of freedom, remember I told you it's row minus 1 times column minus 1. So I have 1, 2, 3, 4, 5 minus 1 times 1, 2 minus 1. You never include your totals. It's just always the raw data. So your totals don't include them at all. The only reason you need your totals is because we're going to be using our expected value. So this data here is just data that you're given. You have to be given data in the beginning in order to be able to run a test. On the AP test, on my test, you will be given a raw set of data. All right, so first of all, it says how many samples do we have and what population? Well, I have 2 samples, one from Meyer, one from Haribo. And then how many variables? I have 1 variable, which is color. So here my Ho would be, the color distribution is the same for Haribo and Meyer gummy bears, and Ha would be the color distribution is not the same. So now we're going to be doing our expected value, and for the expected value, it's going to be, the expected value is going to be the row total times the column total over the complete total. So let me demonstrate that by hand, and then I'm going to show you how to put it in the calculator. All right, so let's pretend if I said, what's the probability of me choosing a random gummy bear and that it is red? Well, you would say that would be 237 out of 754. Then if I told you I had 380 Haribos, then what's the probability of getting a red Haribo? Well, it would be 237, this is the probability of getting a red, and then if I had 380 Haribos, then it would be 237 out of 354 times 380. Well, and that ends up being the row total, 237, times the column total, 380, times the total, which is 754. And if you do that, you will get 119.44. But that's a little bit of data, a lot of work to be able to get this chart. So instead, I'm going to show you how to do it on the calculator. Okay, on the calculator, my calculator is going to look different than your calculator. My calculator has a different screen, but what you're going to do is I'm going to just type any name. You can see any name at all. I'll just type gummies just because it's about gummy bears. And then you're going to have to hit the control button and the button to the right of the 9. And when you do that, mine's different. It's going to bring up a colon and then an equal sign for you. So you have to hit control, button to the right of the 9. Then you're going to hit the button to the right of the 9 again, and it's going to give you a big menu, which is kind of to the left, which kind of looks to the left of my keyboard over here, where it has all these different things. That's what yours kind of looks like. And right in the middle, you're going to see a matrix. Now, I hit the wrong one on mine. I need to hit the correct one because I need to hold mine down and hit this one. And that allows me to, which is the same thing in yours, because if you hit control, button to the right of the 9, it gives you a colon equal sign, and then you hit that same button again, then it brings up a kind of a big sheet to allow you to choose which one you want. And if you hit that center one that has a bunch, looks like a 3x3, it allows you to choose. Okay, so mine is we have 5 rows, remember, not the totals, and 2 columns. The reason you don't have to put your totals in is because the calculator is smart. It can add the totals just fine. It just doesn't know what your raw data is. So I only want your raw data. All right, so if I put this in, I want my raw data, which is right here, 127, 63, 66, 64. Six, 63, 60, and 64. Let me just double check. I'm not sure I got that right. 60, 66, and 64. Okay, I got it wrong order. Oh, I got the whole wrong order. So let me try that again. Okay, so 63. I think it's 66. And 64.
Starting route to 2697.
So then the next one is the Meyer, which is 110, 70, 61, and 68. So it's 110, 70, 61, 68. Once your data is entered, you enter it in the calculator, and now this particular matrix is saved as gummies. Okay, so now we're going to go ahead and run the test. So before I even do my hypothesis test, I'm going to do all my calculator competencies. So you're going to hit menu, and then you're going to do chi-squared two-way test, and then it's going to go gummies. Okay. And here's your test. That's your chi-squared value. And there's your p-value, and there's your degrees of freedom, which was 5 minus 1 times 2 minus 1. All right, so now what you need, though, is you need your expected matrix, which I just told you about. And so to get that, you're going to see above the 9, you'll see variable. It says VAR. And then in that, I need my expected matrix. So you look for stat expected. And there is the 119.443, which was the same that we got before when we multiplied 237 times 380 over 754. And so this is what you get. And there's the instructions on the right-hand side of here. Okay, so that's expected. You also need your component matrix, because remember in the chi-square goodness of fit, you have expected minus observed squared divided by expected. And so this, we would have 127, which would be this one here, minus 119,144 squared divided by 119,44. And then, of course, you would have to do that for all 10 cells. But on the calculator, it's already done it for us. So if you go ahead and hit that variable button again, which is above the 9, and you go to stat, you'll see it stat.component matrix. And those are all my components. And if you add all of those numbers, 0.478 plus 2.242, all of those numbers, you end up getting the chi-squared value, which is 1.677. Now remember, I need all of these values on your test. And what I would do, I mean, you're not going to have 10 values on the test. That's a lot. But what I would do, since you're given the data, is I would turn your table into a observed, expected, and chi-squared, and literally just kind of write them right here. So this would be 119.44, 119.44, and then my next one, I think it was 0.478, so 0.48. So now the reason that you need the expected is because you're going to have to check your conditions with the expected, and you have to show you had the expected values. And the reason you need your chi-squared is because you're going to be having to use this equation to be able to catch your chi-squared value. And when you use this equation, you don't have to put anything in because you're showing that you have all of the data. And obviously, if I just plug the data in, I'm going to be able to get the chi-squared value. Okay, so you can see what my HO is, what I'm looking for. If HO is true, these expected proportions should be the same as the actual data, the observed data. So the expected, not proportions, that really shouldn't say proportions, our expected values, but true, the expected proportions, that I guess that is true, of the Haribo and the Meyer should be the same. But we're going to see actually the expected differences to see how different they are. So let's go ahead and formally put our test together now that we've done everything. So HO is the color distribution for Haribo, and Meyer is the same for the gummy bears. We're going to use an alpha level of 0.05, 5%, and Ha's the color distribution is not the same. We're going to use RILT for our conditions. Random, we have a randomly selected gummies that was given to us. Independent, each gummy is independent from each other, and the groups are independent. I've got a Meyer group and a Haribo group, and they're independent. Large counts, you're going to look for the expected cells and see that all the expected cells and the observed counts and the expected cells are greater than 5, and all the observed are all counts, meaning there's not any decimals. And you can see all of them. And the 10% rule, you're going to go ahead and take the 10% rule. Now, since the conditions are met, do not say normal because it is not normal. It is a skewed distribution. It's skewed to the right, so it's never normal. Do not say that on this one. So I show my degrees of freedom. I list all of my values that I told you that you were going to need. And again, just put it in the current chart. And then you do not need this blue part where I showed you because we already have the chart and we have the formula. You need to make sure that you have the chi-squared value. And then you have the p-value. It looks like I put chi-squared value is 0.795. That's not correct. The chi-squared value is 1.67. So that should be 1.67. 1.67. At the p-value is 0.795. And the degrees of freedom is 4. So because the p-value is greater than 0.05, we fail to reject Ho. We do not have convincing evidence that the color distribution is not the same for the two brands of gummies that we have. The p-value interpretation is assuming Ho is true, there's a 0.795 probability of getting a chi-squared value of 1.68 or more extreme purely by chance. Remember that the chi-squared homogeneity is two populations where the chi-squared goodness of fit is only one population. All right, I'm going to make another video on the chi-squared independence. If you'd like to see that, go ahead and check that video out.